Hi, welcome to this video. In this video, we're going to talk about Microsoft Cognitive Toolkit, or CNTK. Microsoft Cognitive Toolkit is Microsoft's open source deep learning toolkit. It was originally created by Microsoft speech researchers back in 2012. At that time, it was called a Computational Network Toolkit. In 2016, January, we have open sourced the Cognitive Toolkit on GitHub with the MIT license, which is very permissive. Currently, we have about 12,000 plus GitHub stars on the CNTK toolkit, and this is third among all deep learning toolkits. We have 150 plus contributors from MIT, Stanford, NVIDIA, Intel, and many others. So the Cognitive Toolkit is running over 80% of the internal Microsoft workloads. And this includes Cortana, HoloLens, Bing and Bing Ads, Skype Translator, Windows, Office, Cognitive Service, and Microsoft Research. One of the advantages of using CNTK as your own deep learning toolkit is that the CNTK is internal and external identical, which means if you use this toolkit, you will be using exactly the same toolkit as many of these product teams inside Microsoft. So the Cognitive Toolkit is first class on Linux and Windows. It has Docker support, and it has a rich set of APIs. CNTK was mostly implemented in C and C++ for both training and eval. We have a low-level and high-level Python API sitting on top of the C++ API. And it is a very thin layer, and therefore running in Python is also very efficient. We also provide R and C# APIs for both training and eval. We also support UWP, Java, and Spark. We have built-in readers for distributed learning, which is critical if you want to train your deep learning tasks on multiple GPU machines. We also offered Keras backend support since version 2.2. One of the major advantages of CNTK is its speed. In this particular slide, I have this comparison from a university in Hong Kong who had compared basically 5 different toolkits across 4 different tasks. And you can see that across all the tasks, Cognitive Toolkit is the winner in terms of running speed. Of course, for some of the tasks, the difference are quite small, and it might be due to various reader and all kind of small reasons. But for recurrent network, in particular in this case, the LSTM network here, we can see that we are mostly 5 to 10x faster than most of the other toolkits. And that is one of the major strengths of CNTK, because CNTK was originally created by the speech research folks, and there has been a lot of optimization in getting recurrent network to run really fast. Lately, we have released a number of versions for CNTK that includes 2.2 in September and 2.3 in November. In these 2 releases, there has been a number of new features that include HTML version of tutorials and manuals. We have Nico 2 support that allows you now to train really fast across multiple GPUs across multiple machines. We have 16-bit support for NVIDIA's latest GPU Volta. We have integrated MKL DNN, and we have added the Onyx support, which is an open source neural network exchange format that we collaborated with Facebook. We have also added a C# API, R-binding for CNTK, and we have some new APIs in 2.3 for model simplification and compression. We also added a number of new ops and performance improvements and some small API updates. A lot of new examples and also tensor board support. In this particular video, the remaining part of the video, I'm going to focus on the C# API. So the C# API, which was created on top of the C++ API, is a complete API that can do both training and eval. It has over 100 basic operations to build a computational network. The CNTK function is used as a primitive element to build a DNN. So you can build a DNN through all these basic operations and through composition. We support batching, which basically says you can train examples in batches, and this speed up the training process. We have training support that have various learners such as SGD, Momentum SGD, AdaGrad, etc. C# also supports eval, and we have some end-to-end examples provided in C#. Now, I'm going to spend the remaining time give you an example using C# to do transfer learning. For many of you who haven't heard about transfer learning, this is, according to Andrew Ning, the second place after supervised learning for machine learning commercial success. And one of the pain points for training deep learning models is to collect a huge amount of data. With transfer learning, the amount of data required is much fewer. And the basic idea is instead of training everything from scratch, we use a model pre-trained on some other large data sets, for example, ImageNet. Once we use that model, and then we adapt this model parameter slightly for the new task based on some new training examples. Here's a diagram showing how to do transfer learning. So you start with a pre-trained model, in this case, a VGG16 model. And then what you do is you clone the convolution part. This is usually the bottom part of the network. In this figure, actually, it's on the top. So input is from the top, goes through all the convolutions, but we're going to fix all these convolution layers. And then we attach some new layers at the end in order to regress or classify your own problem. In this example, at the end, there is a dense layer of 20, which means you will have your classifier with 20 different classes. With this new model being calculated, you can do a training on new data with your own data. And next, I'm going to give you a walkthrough on the code. So let's take a look at how to use C# to do training and evaluation on a flower dataset using transfer learning. And this is one of the CNTK C# examples provided in the toolkit. So the flower dataset contains about 102 different kind of flowers. And these flowers, of course, each one contains a relatively small number of training examples. What we would like to do is to use a pre-trained model from ImageNet, which is the ResNet 18 model, and then we will use that model and adapt to the flower dataset. So in C#, we started by defining a few folders and map locations. So in this case, the folder of flower is here. And then we have train maps and validation maps, which defines how the images are mapped to labels. And once that is defined as simple strings, we will be looking at how we check, well, if this model has already been trained. If not, we will retrain. Otherwise, we'll just go through the validation pass. So now we start to prepare the training data. In CNTK, there's a concept of mini-batch source. In this case, we create a mini-batch source that contains image and labels. This is an image deserializer. Once we have the mini-batch source, we create a transfer learning model. So let's look at a little bit more detail of how we create this transfer learning model. So the transfer learning model takes input of a base model file, which in our case will be a ResNet 18 model. It contains a feature node name that's inside the ResNet 18 model. What is the input, the name of the input node? And then we have an output node name, which is the output of the ResNet 18 model. And we also have a hidden node name, which is, as we described in the previous slides, that's a place where we decide to cut off. And so underneath, everything underneath below this hidden node, from the input to that hidden node, we'll freeze these parameters. And after that, we will add some layers and then adapt the model to learn the flower dataset. So in CNTK, here are the steps you need to do. You first load a base model. So you load the base model file. Then you define what is your image input and the label input. And then typically for most of the image applications, you need to normalize your input. In this case, we're just subtracting a mean value, 114, and that creates these normalized feature nodes. After that, we're going to look inside the base model and decide, look for which one of the node has a name feature node name, and that's our old feature node. And then we also look for the hidden node name. After that, we're going to clone the CNTK model of the ResNet in this case as a clone with the parameter of freeze, which means we're not changing these cloned parameters. And this clone will be cloning until the normalized feature node to the old feature node. And then after that, we add a new dense layer for class prediction. This is a layer that we're going to adapt these parameters, and then we add two loss. One is the training loss, and the other one is not really a loss, it's a prediction error. When we do training, we typically want to know how well it works on some validation data set. And that is all you need to do to define the transfer learning model. Once the model is defined, we will just set some parameters to prepare for training, and that includes what is our number of mini batches, the mini batch size, the learning rate, the momentum, and some L2 regularization. With all these parameters being defined, we can basically initiate a learner. In this case, we're going to use a momentum SGD learner. And then we initiate and call the trainer. So we create a trainer here with all the things we have created, and then mini batch by mini batch, we are going to get the next mini batch, which is get one mini batch of data. In this case, the size is 50, so we're going to 50 images with their labels. Once we have that, we train the mini batch with all the information we have been provided. After the whole training is done, we save the model, and then we validate the model on some validation data set. And that is pretty much all you need to do in order to do transfer learning with a C#. Thank you for watching this video. If you'd like to know more about Cognitive Toolkit, please go to this website, https://github.com/Microsoft CNTK. Thank you.